Hi, it's Jasio here, and today I'm going to show you how you can measure the speed of light with just a microwave oven, a ruler, and an egg. Now this one definitely requires adult supervision because I had to take down my microwave and kind of mess with the parts a little bit, so you shouldn't do this on your own. So you may be wondering, speed of light, what's that got to do with a microwave oven? Well actually, microwaves, like light waves, are both part of the electromagnetic spectrum. They're both types of electromagnetic radiation that travel at the same speed. So microwaves travel at the speed of light, which is, when we say light, we're usually talking about visible light, which has a lower wavelength than microwaves. And I'll explain what I mean by wavelength in a bit. When I'm talking about waves, first we need to understand what a wave is and what role it plays in our universe. So for anything to happen at all, it requires energy. And energy can travel in patterns such as waves, and there's different types of waves. So when I said wave, you probably were thinking of this kind of wave, this just sort of wavy, squiggly thing. This is a transverse wave. Light moves like this. There's also longitudinal waves. Sound moves like this. This one you can kind of imagine as a big spring or coil compressing and expanding as you go. Now there's many parts to a wave. If we look here, there are the crests, which are the top peaks, sort of like mountain tops. Then there's the troughs underneath, the sort of the lower parts. There's the nodes in the middle, which is where nothing's actually happening. There's no energy here. The amplitude describes how tall a wave is, and the wavelength is how far apart they are. The next type of measurement we need to talk about is frequency. So frequency is how many waves pass within a certain amount of time. So if we look at this is a very low frequency because only 2 waves happen in this amount of time. Here a lot happens, so this is a much higher frequency wave. So earlier when I was talking about wavelength, you can see this has a very large wavelength, they're very far apart. This is a very low wavelength, they're really close together. So we can imagine microwaves looking like this and visible light looking a little more like this. The frequency that a microwave oven runs at is listed on the manufacturer's label on the back. I've turned my microwave oven around and the frequency is listed here under output frequency, which is 2450 megahertz. This is the most common frequency on most household microwave ovens. So chances are your microwave oven is probably operating at the same frequency as mine. How does all this relate to calculating the speed of light? Well, you may know Einstein's famous formula E equals mc squared. C in that formula is the speed of light. Now here's another formula. C equals lambda, this little shape here, which is the symbol for wavelength, and a lowercase f, which is the symbol for frequency. So the speed of light is equal to the wavelength of that wave of light times its frequency. So what we're going to do here is use our microwave to get those values and estimate the speed of light through our own calculations. So a microwave generates a standing wave. So you can kind of imagine this wave just kind of flipping around back and forth in the microwave while it's heating up your food. And then most microwaves operate at the same frequency. So if we can find the distance between these waves and we know the frequency of our microwave, we can use that to calculate the speed of light. And I'll explain how you can do that. When you're microwaving your food, you may not realize it, but there's a wave just sort of oscillating back and forth here. It's not really moving. So to heat up your food evenly, there's a rotating plate usually inside, and that's spinning around making sure the wave peaks and troughs hit your food evenly. So to make this experiment work, I had to stop that plate from spinning. So what I did, and you should not do this on your own, is I removed the spinning part that goes in here, and I also removed the plate that it spins on. Next, I got a smaller plate that was microwave safe and poured the egg whites on. I just kind of poured it evenly, and we're going to put this in the microwave, watch how it cooks without rotating, and we should be able to see the parts that are heated up most intensely, which are the peaks, and the parts that aren't really heated up at all, which are the nodes. So I just put my plate of egg whites in the microwave, and it's not going to be spinning because I removed that plate and gear earlier. I'm going to heat it up for about 15 or so seconds, just until we see some spots starting to cook more than others, and then we'll do some measurements. This is what our plate looks like now with the egg whites, And if you measure the distance between the most melted spots, so like from this spot here that started to melt to this spot here that actually burst in the microwave, it's about 6 centimeters. We're going to do this in centimeters. Could also flip it over and check this spot over here, which is also about 6 centimeters. So we're going to say that the distance between our melted spots was 6 centimeters. Now, if we're looking at our wave diagram here, the distance of our melted spots was 6 centimeters, but to get the whole wavelength, which includes the peak and the trough, we need to multiply it by 2. So our wavelength in this case was 12 centimeters. Now with our formula, we need to multiply our 12 by our frequency, which we already found on the back of our microwave oven as 2,450 megahertz. Megahertz, the M in mega stands for 10 to the power of 6, and hertz is just 1 over a second, so it's an inverse second unit. So we multiply those things together, we get about 2.94 times 10 to the 10 centimeters per second. And if you Google it online, you'll see the speed of light is 2.99 times 10 to the 10 centimeters per second. So we're pretty close. So the speed of light isn't just something that exists in science fiction movies and TV shows. It's something very relevant to our daily lives, as in the case with the microwave oven. And that calculation wasn't that complicated. There were some really big numbers, but the formula was really simple. And I hope that this video sort of taught you the basics of a wave and the different components. We focus primarily on transverse waves, but in another video, we'll talk about sound waves and how they interact with our ears.